Hi guys, we're going to start on chapter 4, which is motion in 2 dimensions. We have a term that we call an object that has motion in the x and the y direction, and we call that projectile motion. So within this, we're going to be using kinematics. So like what we've done so far in chapter 2, I think that really chapter 4 is just more of an application of using the kinematics. We may also see a little bit of 3-dimensional motion in this chapter, but our primary focus will be in 2 dimensions. So if we're talking about projectile motion, then an object may move in both the x and the y direction, and that's what's going to happen a majority of the time. You're going to have something that moves horizontally forward and then also is going to fall due to the acceleration of gravity. So if an object moves simultaneously in the x and y direction, we call that projectile motion or any type of 2-dimensional motion. So first of all, let's talk about some assumptions that we make whenever we have projectile motion, and then we'll kind of decipher the path of projectile motion in this video. And then my goal on Monday is that we'll do our egg drop competition at the beginning of class, and then we'll come back at the end of class and pick up with deriving some different equations for projectile motion. So free fall acceleration is going to be constant over range of motion, and really free fall acceleration should be constant regardless, because we know that free fall means that the only force that will be acting on that object is going to be the force of gravity, which means that its acceleration is going to be 9.80 meters per second. We assume that for the free fall acceleration, for that acceleration due to gravity, it's directed downward, which that should be a good assumption to us. It says this is the same as assuming a flat Earth over the range of motion. So that means that I'm not going to think, if I have an object that I throw over the ground, I know that ultimately overall we think about in a real picture, our Earth is not this nice flat area of space. However, over the small amount of range that most objects that we're going to look at that will exhibit projectile motion, over that range that they'll move, we're going to assume then that there's a flat Earth over that particular motion, okay? It is reasonable as long as the range is small compared to the radius of the Earth. So again, obviously we have curvature of Earth. I'm not going to really consider that just because the objects that we're looking at are going to have a very small range for projectile motion in comparison to Earth as a whole, okay? For now, we are going to neglect friction. We're going to neglect, which really is just going to be air resistance for us right now. We'll add that in when we get into like chapter 6, possibly chapter 5, just whenever we get forces. So right now, air friction or air resistance is negligible. With these assumptions, it says an object in projectile motion will follow a parabolic path. This parabolic path that we will see the object move is called the trajectory. Okay, so you can see that right here. So the object maybe is going to start its projectile motion. So maybe we have a cannon, and then that cannonball is fired. It's moving up this way, and then it's going to come back down. So that parabolic path is just called the trajectory. And we can see here it has some amount of x displacement, and it moves and has some amount of y displacement. So this has to be projectile motion. Okay, so let's talk about the difference between maybe position of a projectile, acceleration of a projectile, and velocity of a projectile, because all of them are going to be different. So if I look at the overall velocity of a projectile, I'm going to follow my velocity vectors. So really, the overall velocity of a projectile and then the overall position vectors or displacement vectors of a projectile are going to be the same. So I'm starting off here, and you can see that I've designated in the blue or purple, I guess maybe it looks like on your screen. You can see that I've designated an axis. So I made my origin to be right where that particular object is about to have it's about to start off on its projectile motion. So V naught is just representing, you can also represent it V sub I, but this V sub 0, or what we would call V naught, is the same thing as an initial velocity. So I have my initial velocity. I'm going to move up along through my parabolic path, but notice what happens, because this is really like a motion diagram. So I have bigger increments here. I'm starting to get smaller and smaller, meaning that this object is slowing down. So the velocity should be decreasing in magnitude as we're moving up. And this right here is going to be what we will call maximum height, or its peak. The velocity at the peak, and I should say, well, we'll get there. Let me hold off on that. Okay, so at its peak, it's going to have to stop. And it has to stop because it has to ultimately change direction, and it's going to start to come back down. Once I stop here, I'm going to start to pick up speed again because it's accelerating due to gravity, right? So I'm going to pick up speed as it's falling towards something that it wants to fall towards. It's attracted to Earth, so that means my speed is going to pick up. So that's why I'm going to start gaining space in between those particular intervals. Until then, finally, we hit the ground, and then that will be our V sub F, or our final velocity. So velocity is going to be tangent to the path for the entire trajectory. But this is overall velocity of a projectile. We can focus on the velocity in the X direction, and then the velocity in the Y direction, which I think we'll do pretty soon. Oh, we do. Okay, good. Let's talk about the X component to velocity, and then we'll also talk about the Y component to velocity, okay? Maybe let's focus on the Y component first, because I think that's just a little bit easier. So overall, here's my overall vector, resultant vector between the Y and the X. Same thing here. Here's my overall vector, so they're bolded in, I think, a bolder red. If I'm starting off here, my velocity in the Y direction is going to be this way. As I continue to move up, so as I go from A to B, I see that at B, that Y velocity vector is smaller than what it was at A. Why would that be the case? That's the case because I am losing velocity, and specifically I'm losing that magnitude of velocity as we move towards the maximum height, because I'm moving away from Earth. I'm moving away from that gravitationally attracted pole. So that means as we throw an object up, acceleration and the force of gravity is going to act on that object, slowing it down. So I should see specifically the Y component of velocity start to get smaller. It should start to diminish. Once I get to maximum height, the velocity in the Y direction is 0. And that's because I'm going to have to stop and change direction. Right now, my velocity, the Y component, is directed upward. I've thrown it upward. That means the velocity is trying to move in an upward direction. However, the acceleration due to gravity is consistently pulling it down. So because I have acceleration acting in the opposite direction, it's slowing that velocity vector down, which is diminishing then its magnitude. So once I get to the maximum height, and this is true for any trajectory, once I get to maximum height, that Y velocity will be 0. And again, we're just looking at the Y velocity right now. I'm now at D, and then we'll go to E. So I'm at 0 at maximum height. At D, we'll see that I've picked up some velocity, but now look what direction it's focused in. Now it's directed down towards Earth. So this had to become 0 because it has to stop and it has to change direction. So now that I've changed direction and I'm directed towards something that I'm attracted to, I'm going to pick up speed in terms of magnitude. So I should see between D and E that the vector at E in the y component should be a larger vector in comparison to D, and I see that. So we've picked up speed or picked up magnitude, and we've also changed direction. So that's specifically for the y component. Let's look just at a general relationship for the x component. I have an x component here at A, here at B, here at C, here's the one for D, and here's for E. What's something that I could say about all of those velocity components in the x direction, especially about their size? They're all the same, right? So whenever we take into consideration acceleration, because we have projectile motion, acceleration due to gravity will act on the object, but acceleration due to gravity only acts in the y dimension, does not act in the x dimension. It's not acting horizontally, it's acting vertically. So because of that, the x component of the velocity vector is unaffected by the acceleration due to gravity. That is huge. This is probably one of the biggest misconceptions that physics students will have, so we want to make sure that we address it now. My y component vectors changed in their magnitudes, in their sizes, in terms of vectors, but I can see that the x component vectors are not going to be affected by acceleration due to gravity. So that means whatever initial x component of velocity that I gave that particular object that's in projectile motion, that's going to be the same that I end with. So I began with a specific x velocity. I'm going to end with that exact same x velocity, okay? Because it's unchanged. It's not affected by acceleration due to gravity. So we're going to see that that is going to stay the same all throughout. Last thing, just on here, let me see. Okay, so it says perpendicular components of motion are independent of one another, just meaning that what's happening with my x direction of, or my x vectors with velocity, doesn't matter about what's happening in the y direction. They're going to be two totally separate kind of systems that we're going to view independently. So now we talked about velocity, let's talk about acceleration. This is another really hard misconception for students, and I'll tell you specifically at which one. Acceleration will point down at 9.8 meters per second squared for the entire trajectory of all projectiles. It doesn't matter where you're at on this parabolic path, acceleration will always be pointed downward. Here's the biggest question that children will always miss. At maximum height, so right here, which is really hard to see because I understand there's like a sun that's right in here at the top. Okay, so right here at the very top, when the velocity is 0 at maximum height, most people will also say that the acceleration due to gravity right there at that moment is 0. But at that moment when the velocity is 0, the acceleration due to gravity is what's making that object stop in its velocity to change its direction. So acceleration due to gravity at the peak, at maximum height, is still 9.80 meters per second squared. The velocity is 0, but the acceleration due to gravity is 9.8. You can't just turn off gravity and the acceleration due to gravity for a split second. It doesn't work that way. So acceleration at every point is 9.8, and at the top it is still 9.8. Okay, so just some terms that I've used, and just to make sure that you have them in your notes. Maximum height is going to be that largest y displacement that we have, or vertical displacement. So we'll see that in just being at the peak or the top of the trajectory. And then when I talk about range, we're going to be talking about specifically the x direction. So I can calculate range in a specific formula that we'll talk about in just, actually we may talk about it on Monday. So starting from wherever my origin was to wherever the end of the projectile is. So how far it moves horizontally, ultimately. So the horizontal component of velocity, let's go back and review. It's constant. So what I start with initially, this is the horizontal or the x component of velocity. It's constant. So what I start with at the beginning is what I should end with. It is not affected, it is not accelerated, and it is not affected or influenced by gravity. And that's because gravity will influence in the vertical or y direction. It is not influencing the horizontal direction. And I know that's kind of hard to think about, because I don't think that you've ever really discussed that gravity only is affecting in a vertical direction. So it may be different for us. We're also going to follow the equation in terms of the horizontal component of velocity, as delta x is equal to vi, the initial x component velocity, times time. But where did I get this from? So you have a kinematic equation. I think it's the last one. I feel like it was number 4. Okay. You have a kinematic equation, delta x equals vi times t, initial velocity times time, plus 1/2 a t squared. You have this. Now, in the x direction is what I'm specifically focused on. So I'm going to give this initial velocity another subscript with an x, just to designate that this is in the x direction. We said that in the x direction, it's not accelerated, because only the acceleration due to gravity is going to do something to the y component of velocity. So because of that, the acceleration in the x direction, so I'm going to write that x there, just to represent that specifically this is the acceleration in the x direction. Acceleration in the x direction is 0. So if that is 0, this whole term is now out. So truly the only way that I could find delta x, which is really what? Range? I could calculate range alone by knowing initial velocity in the x direction and time. So I get this delta x equals initial velocity in the x direction times time from one of my kinematic equations. And I get that just from knowing that the acceleration in the x direction is 0. Okay, guys, I have to go because I have to start the ACT now. I'm already really late. So, if you're taking the ACT, I hope that you do a wonderful job, even though you'll be seeing this after you take the ACT. I will post this on your blog and probably post a few other things on your blog. I will also do egg drop first thing Monday morning, and then I'll write whatever else we have to do on the blog on your post. Okay, guys, have a great weekend. Bye.